Welcome back to the Oxidation Reduction playlist on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe for future videos and notifications. Alright, in this video we're going to be talking about alcohol oxidation, but in simpler terms, what we basically are going to be doing is talking about oxidations of carbon-oxygen bonds. Okay, so let's first take a look at this molecule right here. This is a primary alcohol. We have a carbon atom right here where my mouse is, and we have this oxygen that it's bonded to. That's our carbon-oxygen bond. And when we say we're oxidizing a carbon-oxygen bond, what we're basically doing is we're increasing the number of bonds that that carbon atom has to oxygen. Okay? So, for example, here we have this, at least in this picture here, this carbon is in its lowest oxidation state because it has the least bonds to oxygen. It only has one bond to an oxygen atom. Okay? We go over to the aldehyde, we look at that same carbon. Now it actually has two bonds to oxygen. Technically, a double bond is going to count as two bonds. So we go from one bond from the carbon to oxygen to two bonds to that oxygen. In this carboxylic acid over here, which is the highest oxidation state shown, the carbon atom now has three bonds to oxygen. One going down to the OH, and then two bonds to this oxygen over here that represents the carbonyl. So, the basis is this hierarchy of carbon-oxygen bond oxidation state. In fact, when we talk about oxidation of alcohols, there's three things that really play a role and you need to understand so you can answer questions. One, you do need to understand the hierarchy of oxidation state for carbon-oxygen bonds. We have alcohols right here, which are the lowest oxidation state, which can be oxidized into aldehydes, and then aldehydes can be further oxidized into carboxylic acids. If we're doing reduction, which we'll cover later in other videos, reduction goes the reverse direction. We would start with a carboxylic acid, potentially, go down to an aldehyde, and then reduce that to an alcohol. So understanding the hierarchy of these oxidation states is critical. The second thing that's important to understand are the reagents. Some reagents are what we call weak oxidants, and others are called strong oxidants. We have that shown up here. The second thing that's important to understand is what each set of reagents do. For example, we have weak oxidants, such as PCC. We also have strong oxidants, such as chromic acid, H2CrO4. And understanding what each of these reagents is characterized as will strongly help you determine what products are formed when we react a particular alcohol with the oxidant. The other thing that's important to understand is being able to classify the alcohol as primary or secondary. And hopefully you'd be able to do this by now, but notice that this carbon, the carbon that we'd be oxidizing, only has one carbon group attached, therefore it's primary. This carbon down here has two carbons attached, therefore it's secondary. The nice thing about this, as we'll see on the next slide, we don't actually have to worry about tertiary alcohols as they do not react through any of these. All right, so what we're going to do is we're going to take another look at alcohol oxidation with this figure, and then in the next set of videos we'll go over specific reagents. First we'll do weak oxidants, and then we'll do strong oxidants. Again, we have the lowest oxidation state of each type of alcohol shown here at the bottom. This is a primary alcohol shown here. This is a secondary alcohol in the middle, and then on the right we have a tertiary alcohol. Now to make this easy, tertiary alcohols don't react with these reagents at all. So if you see a tertiary alcohol, so 1, 2, 3 carbon groups attached, there's no reaction with either a strong or weak oxidant. However, primary alcohols and secondary alcohols will both react. Now, I will go ahead and preface this here and then we'll discuss it more in the next video. Weak oxidants. The best example, which is the most common, is PCC. In fact, we'll have a whole video on that one. Weak oxidants, no matter whether or not you're dealing with a primary or secondary alcohol, PCC and other weak oxidants will always turn this carbon-oxygen bond into a carbon-oxygen double bond. Notice if we start with a primary alcohol, this carbon-oxygen single bond, if we use a weak oxidant, gets converted into a carbon-oxygen double bond. In this case, because it was a primary alcohol, it becomes an aldehyde. If we start with a secondary alcohol, we take a weak oxidant, and it converts this carbon-oxygen single bond into a carbon-oxygen double bond. Okay? Now, strong oxidants will do something different depending on whether you start with a primary or secondary alcohol. If you have a secondary alcohol, a strong oxidant will do the same thing as a weak oxidant would. A strong oxidant such as H2CrO4, which is sometimes referred to as a Jones oxidation, will still convert this carbon-oxygen single bond into a carbon-oxygen double bond. Okay? So, if you have either a weak or strong oxidant and you react it with a secondary alcohol, no matter what, you're going to get a ketone. However, if you start with a primary alcohol and you use a strong oxidant like chromic acid, it will automatically oxidize it all the way up to a carboxylic acid. Okay? So let's take a look back on this slide. So if we start with a primary alcohol, if we were to just use a weak oxidant, a weak one, we would only go up one oxidation state to this aldehyde. So the weak oxidant, an example of that where we terminate at an aldehyde would be PCC, which we'll cover in the next video. However, if we start with a primary alcohol and we use a Jones oxidation, which I'll remind you was H2CrO4 chromic acid, which we'll cover in another video, the primary alcohol would oxidize all the way up to a carboxylic acid. Okay? If we're dealing with a secondary alcohol, it does not matter whether we're dealing with a weak or strong oxidant. So, in other words, with a secondary alcohol, we could either be dealing with a strong oxidant such as chromic acid or PCC. It does not matter. We'll always get a ketone when we do that reaction. Okay? So the main things to remember are, first of all, you need to be able to identify if you're dealing with a primary or secondary alcohol, and then recognize what the reagent does. Okay? Are we dealing with PCC or a Jones oxidation? A PCC is a weak oxidant, which should only, regardless of what we're dealing with, should only take this carbon-oxygen single bond up to a carbon-oxygen double bond, as shown in the aldehyde and the ketone right here. However, if we're dealing with a strong oxidant, then it's going to depend on whether or not we have a primary or secondary alcohol. Okay? So with a primary alcohol, if we use Jones oxidation or chromic acid, we'll oxidize all the way up to a carboxylic acid and bypass the aldehyde. We won't be able to isolate this. However, if we have a secondary alcohol and we do a Jones oxidation, we will get a ketone out of that. Okay? And we cannot do these reactions on a tertiary alcohol. Okay? So, join us in the next video when we discuss PCC and DCM, which is a set of reagents that is a weaker or weak oxidizing agent that we can do on alcohols. See you in the next video.